Hi Year 12, so let's have a look at question 9. Two players are playing table tennis. A player A hits the ball at a height of 0.24 metres above the edge of the table, measured from the top of the table to the bottom of the ball. The initial speed of the ball is 12 metres per second horizontally. So this bit is crucial. You've got to think about the direction. Okay, so assume air resistance is negligible. Show that the time taken for the ball to reach the surface of the table is about 0.2 seconds. Okay, well, we know that there's only one ball and it's completing the motion of the dotted line, okay? And in that time, it falls 0.24 metres vertically, and it's also going to travel a distance horizontally as well, okay? The horizontal velocity is the one that we know, so the 12 metres per second cannot be put into the vertical Suvat equation where we know acceleration is g. That's not something we can do because it wasn't moving at 12 metres per second initially in the vertical plane. It was doing that in the horizontal plane. But we do know that the time taken to take this vertical path will also be the time taken to complete the horizontal distance. So those times are the same. So vertically, what we know is that the displacement and the distance travelled is 0.24 metres by the time that it reaches the table. We know that it has no initial vertical velocity because we're told that the entire speed is horizontal. So vertically, it's not moving with any velocity. So U is 0, A is 9.81, and then it's a case of choosing the right Suvat equation. So S is ut plus a half at squared. U is 0, so we cross this out. A is acceleration due to gravity, and we end up with getting S is 0.24, and then we can get T squared just through plugging in. So we've got S, which is 0.24, is a half gt squared, so half is 0.5, g is 9.81, then t squared. Rearrange for t squared, and we've got 0.24 over 0.5 times 9.81. If we square root this value, we get 0.22 seconds, which is approximately 0.2 seconds, and it has been proven. In 9b, it asks you to sketch on the axes a graph showing the variation with time of the vertical component of the velocity until it reaches the table surface. Take g to be 10 metres per second squared. Okay, well, this is a velocity time graph, so the gradient is the acceleration. Okay, we know that because that's just what the gradient of a velocity time graph is. So if we are told that g is 10, then the acceleration value is 10, which means that the gradient of the graph needs to be 10. So you got 1 mark for it being a straight line and 1 mark for the gradient being 10. So you can see it needs to pass through 2, 0.2 and 1, 0.1. From here, it's HL questions only. So in question 10, we've got a beam of coherent monochromatic light incident normally on a single slit. The diffraction pattern is observed on the screen. So you can see O, P and Q. O is the point directly opposite the slit, so that's where we know we'll get our central maximum. Excuse me. And then P and Q, we're told that they are the first minima on either side of the central fringe. So you can see I've just sketched over the top what I expect to see in terms of intensity with position on the screen. And they give you a distance OP being X. So it asks you to sketch on the axes a graph to show the variation of the intensity of light with the distance from point O on the screen. Your graph should cover the distance range from O to 2x. Well, we are told that P is a minima and O to X is the distance between O and P. We are told that. So we know that at X we are at position P, so we must be at a minima. So we need to have put a minima at X on our graph, okay? And you got 1 mark for therefore going from maximum intensity at O, because that was your central maximum position, decreasing down in a smooth curve to 0 at that point, okay? And then your second mark comes from drawing your secondary maxima, and your next minimum will be at 2x. And the value of the secondary maxima could not be larger than 0.3 I0. We did discuss this when we were going through like the minutiae of what they want from graphs, okay? In 10B, early theories of light suggest that a geometrical shadow of the slit will be observed on the screen. Explain how the diffraction pattern formed on the screen provides evidence for the wave theory of light. So, what this question is basically asking is, why is it that when we have a slit here, on the screen we don't just see a rectangular block of light? So what we have to say is what we see instead, and then how we can explain why we see that. So 1 mark comes from saying that the diffraction pattern has a maxima and a minima. And then the 2nd mark comes from saying, well, this can only be explained by the superposition of waves. Okay, so that was pretty simple in terms of what you needed for the marks, but lots of you didn't quite get that. So I would make a note that is a very common thing to have to explain. So 10C, sorry, this was backwards and forwards over the page. The printing wasn't ideal here. The following data are available. So you've got wavelength of light, lambda, distance between slit and screen is 2.4 meters, and then the width of the slit is 0.1 millimeters. So I've just labelled those up. And it asks you to calculate the distance PQ. So I need to go back to the original picture, which is here. So we are looking for this distance, okay? P to Q is the distance from the centre to 1 minima multiplied by 2, okay? And we know we can use our single slit diffraction equation. Theta is lambda over B, gives us the angle to the first minima. Okay, so to go from O to P, so if we remember on the screen, O was in the centre, P was up here, Q was down here, our slit was directly opposite O. Theta is the angle between O and P, okay? And we do that by taking the wavelength and dividing it by B, the slit width. We were given those values on the previous page. We do not need to put our calculator into radians for this. That's not the case. We are doing a length divided by a length to give us a value that happens to be measured in radians. Okay, the value that we get just by dividing these numbers is a value measured in radians. The calculator doesn't need to be put into radians here. Okay, so you get 5.9 times 10 to the minus 3 radians. That gives us the angle out to P. We need to double that to get the angle to Q. Okay, so we double that and we get 0.0118 radians. So now essentially what we have is a small angle approximation, although we don't actually have a right angle triangle, because our angle is so small in comparison to our distance between our slit and our screen, we can use the small angle approximations and we can say tan theta is approximately theta, which is equal to the opposite over the adjacent. Okay, we have the adjacent because that's the distance from the slit to the screen, that's 2.4, and then the distance that we calculate as the opposite will now be P to Q. Okay, so what we're going to do is take our value of theta between P and Q and multiply it by 2.4. Okay, and we get 0.028 meters. In 10D, the single slit is replaced by a double slit, so we know already we're going to see a modulated interference pattern. The width of each slit in this arrangement is the same as the width of the single slit in A. Outline how the intensity variation observed between points P and Q will change. Okay, so it's 2 marks, so we need 2 points. The examiner report, this was really interesting, said a number of students didn't bother to draw a diagram. And where there is physical space in the box or next to some lines to draw a diagram, you should do that, because even if your words are terrible, if they can see what you mean in the picture, they will give you all the marks. So please take a chance to draw a diagram alongside it. So well done if you did that. So if we now have 2 slits rather than 1, more light can reach the screen full stop. Okay, so the intensity at O, the central maximum, is going to increase. Okay, that was the first mark. And then the second mark is that we will now see a series of maxima and minima in between where we originally had O, our primary maxima, and our first minima at X, that was where P was, okay? In between there now we're going to have secondary maxima and minima because of the double slit interference. So we want to describe that as a series of maxima and minima seen where the intensity decreases to 0 as you move away from O to P and then also O to Q, so it would work on both sides. Okay, so you can't just draw the shape, you do have to label things up so that they understand that you know that the maxima and minima are between 2 points that you've figured out. So that was what the 2 marks were for there. Okay, in 10E, 3 marks. The light source actually emits 2 wavelengths of light. The average wavelength is 590 nanometers, and the difference between the 2 wavelengths is 0.6 nanometers. A student attempts to resolve the wavelengths using a diffraction grating with 750 lines per millimeter. The incident beam is 2 millimeters wide. So we need to work out how many lines the beam is actually travelling through. We know that the beam width is 2 millimeters, and in each one of those millimeters there will be 750 lines. So the total number of lines, N, is 1,500. Okay, and then I've just listed my 2 equations from the data booklet about resolution. So it says, comment on whether this diffraction grating can resolve the wavelengths in the first order spectrum. So we're going to look at the first series of equations from the data booklet and make it applicable to us. So we know that resolvance is equal to wavelength over the change in wavelength between the 2 sources equals to Mn, where N is the number of slits illuminated and M is the order of diffraction. So these 2 things must be equal because they are both equal to R. So I can rearrange this for delta lambda, the smallest difference in wavelength that can be resolved. And that's equal to the wavelength over Mn. So I'm going to take this equation, okay, delta lambda is equal to lambda over Mn. It asks for when it is in the first order spectrum, so M is 1. N is the number of lines that are being illuminated, and then this is your wavelength that you're trying to see whether you can resolve. So you find that the smallest resolvable difference in wavelengths that can be resolved when we're looking at the smallest one being this value turns out to be 0.39 times 10 to the minus 9 nanometers. Okay, we go back to the original question and it says that the difference is 0.6 nanometers. Well, if the smallest resolvable difference is 0.39 nanometers, sorry, I should just say nanometers, then we know that because this is smaller than the value that we've got, we can resolve the sources. Okay, so we can. But you need to show that with your maths. 11A, this was done pretty well, so well done. State what is meant by the Doppler effect. 2 marks, 1 for each of these points. It's the change in observed frequency. Do not say wavelength, you will not get the mark. Okay, it's perceived frequency. When there is relative movement between a source and an observer, 1 mark. 11B, a plate performs simple harmonic oscillations with a frequency of 39 Hz and an amplitude of 8 centimeters. Show that the maximum speed of the oscillating plate is about 20 meters per second. So you can see that I'm already playing around and thinking about things I know that are linked to frequency and speed, but they're not actually relevant to the question. Sometimes that's how you approach questions until you find what you actually need to be doing. So in your data booklet, you will find for an object in simple harmonic motion that the velocity can be found by plus or minus omega root x naught squared minus x squared, where x naught is the maximum amplitude in your simple harmonic motion and x is your displacement. And we can see that the maximum possible value is going to be when x is 0, so when we're going through the equilibrium point. So this equation simplifies to Vmax is omega root x naught squared, which is omega x naught. Omega is your angular frequency, is 2 pi f, or 2 pi over t, and x naught is your amplitude. So I can express that as 2 pi f a, x naught is just the amplitude, And then it's just a case of subbing in, because we've got the frequency was 39 hertz and the amplitude was 8 centimeters, but you need to put that into meters, and you get 19.6, which is approximately 20 meters per second. 11C, now this was really hard. This was a tricky one to get your head around. So, sound of frequency 2400 hertz is emitted from a stationary source towards the oscillating plate in B. The speed of sound is 340 meters per second. Determine the maximum frequency of the sound that is received back at the source after reflection at the plate. So, I need you to split this whole scenario into two stages. Stage 1 is where we've got the source is stationary, the plate is the observer is receiving the sound, and the plate is moving. So in step 1, the plate is a moving observer. Upon reflection, the plate becomes the source, and the source originally is actually now the secondary observer. So we have in stage 1 a moving observer, and then after reflection we have a moving source. So this is double Doppler effect. We've got to do it twice. Okay, so what we're going to do is find the maximum frequency that can be perceived by the moving observer plate, and then we take that new frequency perceived and we find how much that gets shifted to its maximum value when it is then a moving source. So in stage 1 we have a moving observer, so we take our moving observer equation. Okay, that's in your data booklet. We know we have to choose plus or minus. We know that we're looking for f dash, the perceived frequency, to be as large as possible, therefore we choose plus. Okay, so we take the original frequency f, we take the speed of sound plus the speed of the moving observer, which is 19.6, or 20 if you chose to carry on with 20. This number is what you got from part B. Divide that all by V, and you get 2538 hertz. This is now the reflected frequency maximum by the plate possible. This frequency is then being reflected back towards the source, and we need a new perceived frequency, because while we have that frequency being reflected, the plate is also moving. Okay, so we've got a moving source emitting that higher frequency. So we're going to take the moving source equation. I've called it f dash dash. This is the second perceived frequency at the end, where f dash was the reflected frequency that we've got here. Okay, but we're just substituting into the normal equation. So if we have a moving source, the equation becomes fv over v plus or minus u of the source. And I've just replaced f here with f dash, because it's now the frequency that we had from before. Hopefully you can figure that one out for me. We know that we're looking for the maximum frequency possible received back at the source, so therefore we need the denominator to be as small as possible, so we choose minus. And then we take the reflected frequency and we then double Doppler effect that, essentially, by taking V, which is 340, over V minus U of the source, which was 19.6. And we get 2694 hertz as your maximum, and that approximates to 2700. So significant figures don't matter too much there. But that was a tricky question. You just had to recognise that it was a double Doppler effect. In 11D, the graph shows the variation with diffraction angle of the intensity of light after it has passed through 4 parallel slits. So this is essentially a diffraction grating. Okay, so you can see you've got your position, and then you've got primary maxima listed here, and then you've got secondary maxima listed as well. The number of slits is increased, but their separation and width stay the same. All slits are illuminated. State what will happen to the angular position of the primary maxima. So when we are looking at diffraction gratings, we can use n lambda is d sine theta, and I can rearrange for sine theta. because I'm looking for angular position. So I'm interested in seeing what happens to sine theta. And that is equal to n lambda over d. Well, primary maxima are not going to be affected in terms of their angular position because n, lambda and d have not been changed. If you go back to what they say stays the same, everything has stayed the same. So theta has not been changed, therefore no difference. Okay, so all unchanged, no change. Okay, now the thing that is frustrating for me is when we teach diffraction gratings, the optics and the physics behind them are actually so complicated. We do you a disservice by having to make you answer these questions, I feel, for IB, because we kind of fudge it a little bit. The easiest thing I can do for you is I have printed you all this sheet that kind of revises what we know about diffraction gratings, and you can see single slit, double slit, and then moving on to 3, 5 and so on, and you can look at how the pattern changes. And the easiest thing that's going to make sense for you is that you just memorize how the pattern changes, and I've given you a little description. I've also added a picture, hopefully you can see that, it's not that clear, of how the pattern changes. Is that a bit clearer there, down there? As we add more slits. So you can see we've got our primary maxima from our single slit modulation over the top, but within there we've got secondary maxima. So you can see, if you look super closely, we've got primary, secondary, maxima within there. And then I've added a little description for you, and we're going to add this into your folder. So, when multiple slits are introduced into the system, such as in the case of a diffraction grating, the overall intensity distribution, so what the intensity looks like where, due to the interference effects, changes. So, the primary maxima remains bright and well defined, but secondary maxima become less intense as the number of slits increases. So if I pull this down, hopefully that will be a little bit clearer for you to see. So as we move down, our secondary maxima are becoming less well defined because the intensity has dropped. Okay. This decrease in intensity occurs due to interference effects. When light passes through multiple slits, each slit acts as a new source of waves that can interfere with one another. The constructive interference between the waves from different slits creates the bright maxima, while destructive interference leads to the dark minima. As the number of slits increases, secondary maxima become narrower and closer together. This narrowing occurs because the path length difference between waves from adjacent slits decreases as the number of slits increases. Consequently, the constructive interference that creates the secondary maxima becomes less pronounced, resulting in a decrease in their intensity. So you can hopefully see how the interference pattern changes. So the primary maxima that you are seeing, so here, are becoming narrower as we add more slits. So the width has definitely got narrower. Okay, so more slits, primary maxima width decreases. You should also see that the secondary maxima that I'm pointing out here are decreasing in value as we add more slits. Okay, so the intensity of the secondary maxima drops. So, going back to the paper, if you can just remember these are recall questions because it's just memorizing what that pattern looks like. State what will happen to the width of the primary maxima. You just need to say decrease for the mark. That's all you needed. Primary maxima become narrower as more interference occurs. I tried to go into this in like mathematical detail. You can see I probably erased things. I actually just don't think it's worth our time. It gets annoyingly frustrating to see all the approximations, and we kind of skim over the math slightly, but we don't do it properly. And I think at this point, for you and being successful in IB, rather than getting frustrated with not being able to spend enough time to figure this out properly and make sure you've really got this, I think let's just make sure that we know what happens to the pattern. In 11F, state what will happen to the intensity of the secondary maxima. 1 mark just for saying the word decreases, but I've just said increasing the number of slits increases. The amount of interference occurring destructively, so decreases. It does come up quite a lot, so I am glad I still included this question, by the way. I just know it's frustrating, but I have printed this off for you all so that you've got it. Excuse me. In 12A, a parallel plate capacitor of capacitance 1.5 times 10 to the minus 10 farads is made from two metal plates separated by an air gap of 1 millimetre. Don't forget to convert that into meters first. The capacitor is initially charged to a potential difference of 24 volts. Calculate the energy stored in the capacitor. Well, energy is a half CV squared. 0.5 times the capacitance multiplied by the voltage squared gets you 4.3 times 10 to the minus 8 joules. So we've got our parallel plate capacitor. We've found out how much work can be done by that capacitor. That is the energy stored. In 12B, wait for it to focus, the charged capacitor is disconnected from the voltage supply and the separation between the plates is increased to 4 millimeters. Explain the change, if any, to the potential difference, so the voltage across the plates. Okay, well, we can hopefully see that electric field strength is force per unit charge, which is voltage divided by separation distance between the plates. We also know that the capacitor has a capacitance according to the equation from your data booklet here. Okay, so hopefully you remember we've got permittivity, the cross-sectional area of one of the plates, and then the separation distance between the plates. So the separation actually impacts the capacitance, okay? It's increased from 1 millimeter to 4 millimeters. That's a factor of 4 change. If D is multiplied by 4, then the capacitance decreases by a factor of 4, okay? We know that voltage is, if we take our, this is from our Q equals VC equation, voltage is the charge per capacitance, okay? The total charge available in this system is unchanged, okay? It's the same scenario, it's the same setup, we've just physically pulled the plates apart, okay? So charge is unchanged, but capacitance has changed by a factor of 1/4. Capacitance is on the bottom of the equation, so if this is changing by a factor of 1/4, then this whole thing changes by a factor of 4. So therefore the voltage across the plates is now going to be increased by a factor of 4. Okay, what that really means in reality, think about it with common sense, is voltage is joules per coulomb. It's the amount of energy required per unit charge to keep it on the plate. If the plates are separated, we know it requires more work to keep those negative charges built up on one of the plates because we no longer have the pull. So if you think about the capacitor where one plate is positive and one plate is negative, we've built up all our electrons on one plate. They repel each other. They don't want to be near each other. But the closer they are to the positive anode on the capacitor, the more they can overcome that repulsion because they've got a stronger pull of attraction to the plate. But because we've now moved the plate away from that positive plate, those electrons no longer have that nice attractive pull in the same value. They have that in a decreased value, and so there needs to be more work done per charge to keep these electrons on the plate where they don't actually want to be near each other. So it logically makes sense that the voltage has to go up. Okay, so we know it's by a factor of 4. We take our original value, multiply it by 4, and we get 96 volts. And then it says, determine the work required to increase the separation of the plates. Okay, so we know that there had to have been energy put in order to allow these charges to build up on this plate if the plate is now further away from the positive plate. So the work done is going to be the new total energy minus whatever energy we already had. So we got our initial energy in part A. We need to find the energy in our new arrangement. So we know that energy can be found by a half QV, okay? And we know that Q remained the same, but V went up by a factor of 4. So the energy total increased by a factor of 4. So the energy in the new arrangement is this one. The energy in the old arrangement was this one. So the difference is the extra energy that had to be put into the system. Okay, and we get 3 times 4.3 times 10 to the minus 8, and our final answer is here. In 12D, the capacitor is then discharged through a fixed resistor. The initial current in the resistor is I0, and the time constant of the circuit is tau. Draw on the axes a graph to show the variation with time of the current in the resistor. Okay, we know that we have exponential decay with capacitors. I is equal to I0 e to the minus lambda t. Okay, we've got this. We could replace this with voltage. We could replace this with charge, but it follows the same pattern. We have exponential decay. Initially, during discharge, all those electrons built up on that plate, they are repelling each other. There's this big push, right? There is this big push for those electrons to move. But as they redistribute onto the positive plate is becoming more negative, which actually opposes the subsequent electrons trying to move back onto that plate. The whole thing slows down. So we know that tau is the time constant, RC. We know that this is a fixed value for a particular capacitor in a particular resistance in the circuit. Okay, we have a total resistance of a circuit, we have the total capacitance. When we multiply those two together, we proved this in class, this works out to be the time constant, and because it is a fixed value, we also saw that it happened to be the time taken for I to discharge to about 63% of its original value. So hopefully I'll do a little sidebar here. I over I0 is equal to e to the minus lambda t. So we've got then I over I0 is equal to minus lambda t. Okay, and so we did this whole derivation. Go back and have a look at it. Okay, sorry, I shouldn't say lambda. It's been a long day here already. That should say tau. It's tau. Okay. We know then that we have this value tau as a time constant is a fixed thing. This is just something that you need to have remembered. We said this, we wrote this down in your books. So for 63% of the original value to have been discharged, we must have 100 minus 63% left. So we've got about 0.37 of the original current at that time. And so at that time, you need to find about 40%, and it needs to be approximately here that you've got your data point, and then from there you move your shape through and you show an exponential decay. So you got 1 mark for it being an exponential drop and 1 mark for having an approximate value of tau, because this was a number that you just needed to remember. In 12E, a diode bridge rectification circuit is often modified by adding a capacitor in parallel with the output load resistance. Describe the reason. Lots of you only got 1 out of 2 here, because you really just talked about the smoothing. So the capacitor smooths the output voltage, 1 mark. Why is that helpful is the 2nd mark. This ensures that the voltage output stays relatively constant instead of fluctuating between Vmax and 0 repeatedly in an AC supply. So you can just pause that and add that in if you didn't get it. Okay, 13A. You've got a square loop of side 5 centimeters, turn that into meters, enters a region of uniform magnetic field at t equals 0. The loop exits the region of magnetic field at t equals 3.5 seconds. The magnetic field strength is 0.94 Tesla and is directed into the plane of the paper. The magnetic field extends over a length of 65 centimeters. The speed of the loop is constant. Show that the speed of the loop is 20 centimeters per second. This one just required a bit of extra thought. Okay, we know that this part of the loop starts at this position, 0, and at t is 3.5 seconds, the same part of the loop is here. It is not at 65. You have to add 5 centimeters because it's a square loop. That's 5 centimeters. So the total distance that whole thing traveled was 70 centimeters, not 65. So we just do 0.7 over the 3.5 seconds, gets me 20 centimeters per second. Okay, in 13b, sketch on the axes a graph to show the variation with time of magnetic flux linkage in the loop. Okay, well, we know that the time it's going to take for the whole loop to enter the field is the 5 centimetres of the loop divided by the 20 centimetres per second, gives me 0.25 seconds. And as it's entering at a steady speed, the amount of flux within the loop is increasing uniformly during this time, okay? So therefore, flux is increasing at a uniform rate between 0 and 0.25 seconds, at which point it's fully within the field, so the amount of flux doesn't change during that time. Once we've reached the final point, it's going to take the same amount of time to drop from maximum to 0 flux. So for the last 0.25 seconds, it drops from maximum to 0. Okay, so that's what your graph should have looked like there. Sketch on the axes a graph to show the variation with time of the magnitude of the EMF induced in the loop. Okay, well, EMF is rate of change of flux linkage. It will only induce an EMF if there is a rate of change of flux. This only happens during the first 0.25 and the last 0.25. Okay, we know that the rate of change of flux was constant because it was increasing linearly. So the value is going to be constant. The rate of change of flux linkage is constant. So during that time, we've got a fixed value of EMF. Okay, so we should have a square wave there. In 13D, it says there are 85 turns of wire in the loop. Calculate the maximum induced EMF in the loop. So again, we take rate of change of flux linkage. This time I've expressed flux as BA because that's more helpful to me. That's what flux is, we know this. We need N for the number of turns, so we've got 85, lots of B, the field strength, multiplied by the area. In meters, that's 0.05 squared, because it was 5 centimetres by 5 centimetre loop, divided by, and the time it took for the EMF to be induced in that time, it changed that amount of flux that we have here as a maximum. We went from 0 to BA in 0.25 seconds. You do not do 3.5 here. Okay, the change of flux did not occur over 3.5 seconds, it occurred over 0.25 seconds, and that gets me 0.8 volts. In 13E, the resistance of the loop is 2.4 ohms. Calculate the magnitude of the magnetic force on the loop as it enters the region of the magnetic field. Okay, so we can immediately work out the current that is being generated because we've just found the voltage induced. We can divide it by the resistance, and we know that we've got 0.33 amps flowing. Okay, as it enters the region of the magnetic field, if I go back to the picture, at the instant where it enters, the only part of the loop that's actually within the field is going to be this section. Okay, so we actually only have a 5 centimetre length that is considered. So the magnitude of the force, F, is BIL. We have the field, we have the current that would be flowing through, and we have the length of the conductor that would be moving into the field. But we also have to remember there are 85 loops. We've got 85 lots of them. So lots of you got 1 mark because you forgot to multiply your value by 85, and we get 1.31 loops. And then that's it. The last page you didn't have to do.